Okay, here the problem is minimum jumps to reach the end via prime teleportation. Okay, so what it is saying, like it is again a jumping kind of array, jumping in the so array of length, nums of length n. So we have to start from index 0 and my goal is to reach n minus 1. Okay, so I can jump in two ways. So either I can jump to adjacent any of the adjacent index like I plus 1 or I minus 1 if it is inside the bound, like within the bounds, then we can jump only. Otherwise, there is another case. Like if my current now my index is a what is the number present in the index is a prime number. In that case, I can jump to any other index. So if that number present in that index is divisible by this current prime number, I'm coming to I will explain this problem. But before that, let's see what are the length. Length is 10 to the power 5, and sorry, length of the line is 10 to the power 5. So it can't go for big of n square approach. It is not possible. So we have to do less than big of n square. Big of n is also not possible for this case. You will understand why, but it's not possible. 10 to the power 6 is a maximum length. Okay, fine. Okay, let's see the example. So example, if I see, so these are 1, 2, 4, 6. So 1, 2, 4, 6. So this is the example, right? So from 1 I can go to 2, from 2 I can go back to 1, or I can go to 4, 4 I can come back to 2 or go to 6. Now coming to the that one extra case, like if my any element is a prime number. Here what are the prime numbers? Two are the prime numbers, right? So if that is my prime number, then what are the cases I can go where I can to I can go any other index if the element present in that index is divisible by 2. So what are the index what are the elements that are divisible by 2? So there are 4 and 6. These are the two digits that are divisible by 2. So I can go either 2 or I can go to the 6. So at the end, what I have to return? I have to return minimum number of steps I need to reach 6. So here, what are the cases? I'm starting from this index. My goal is this index, this one. Like this is not an index. This is from this digit and this digit. I can go to 2 and 2 to directly go can 4 and 6, or I can do what? From 1 I can go to 2 and directly go to 6. So two possible outcomes, and these two are actually same. These two. I'm removing this one, and this is a course, right? Now here another example, like 2 3 4 6, like 2 3 4 7 and 9. The thing is, here examples are in sorted, but it is not guaranteed that it's a sorted array. Please keep it in mind. It's not a sorted array. So in this case, what are the possible cases? I can go 2 to 3, 3 to 4, or 3 to 2 also, then 4 to 3 or 4 to 7, and 7 to 4, 7 to 9. Then what are the possible cases? 2 is a prime, I can go to 2 to 4. 3 is a prime, I can go to 3 to 9. So what are now how could I reach? So first I can reach from 2 to 3, 3 to 4, 4 to 7, and 7 to 9. How many steps? 1, 2, 3, 4. 4 steps I need. So obviously it is not my optimal solution. So see what are the other cases. I can go 2 to 4. Okay. 4, 4 can 7, 7 to 3. So how many hops are there? 2 to 4, 4 to 7, 7 to 9. 3 hops. So this is also not my optimal solution. What are the other cases I can go? I can go 2, 2 to 3, and 3 to 9. Right. So 3 to 9. So this is my optimal solution. 2 to 3, 3 to 9. This is my optimal solution. So in this case, I can go to I can reach my goal within 2 hops, 2 to 3 and 3 to 9, 2 hops. So this is my optimal solution. So, so see this pattern. This is what it looks like. Isn't it look like a graph? Doesn't it look like a graph? Yes, it is looks like a graph. And how could I find, like this is the cost of one and this is an undirected graph, right? So you don't think like this is it is one way pattern. There may be possibility to assume there is a possibility. This is the graph. Okay. So there are many possibilities, like, and I didn't have that example, but I saw this example. That I have to go here, then I may go here, and then here, and example there are many more steps are there, and then I can jump back to this place. So there are many examples like this. This is the graph, like 1, 2, 3, and 4 hop I can reach. Okay. This could be the shortest algorithm. Okay. So another example, it could be possible, like here, here, next there are the graphs. So assume they are the lines are connected by this way. Assume these lines are connected by this way. Okay, so this is our typical case, like each node is collected or each digit is connected to its adjacent digits. So these are the cases, but assume there are some numbers, so I can reach from there to that side. So this is the assume I can from jump to here to here, then I can jump here to here, then go back to here, then I can directly jump here. So how many steps it is taking? It is taking fast hop, second hop, third hop, and fourth hop. Within the fourth hop, I reach my outcome, right? So this is the minimum element I am taking. So see, this is the how we could do. This is how we could do. So you want an example? Let's put an example. Let's say 2. Then here let's say put as 3. Here let's say put as 4. Here let's put as 5. And here let's put as 10. Okay. Not 10, 9. Okay, and here let's put any number like 7, 11, 13. I am intentionally putting is at prime numbers because I can't reach actually in that cases. So here, see here. So normal step is 2, 7, 3, 5, 4. If you can't go there, so I can go 2 to 4 direct hop, 4 to 5, 5 to 3. I can come back. So 5 to 3, I can go. Why I can? How can I go 4 to 5 or 5 to 3? Because I can move to the adjacent places. And 3 to directly I can jump to 9. See, this is the one cases. You cannot reach this way, right? So I may have to track back, correct? So this is a simple graph problem, if you understand. So graph, now in the graph problem, what is specific problem? Now, what I put is shortest path. Shortest path, this is why shortest path I am saying, because the cost of the path, I need actually cost of the path. And the cost of the path is what? Because each step I have to count, this is the step, and this is one step is count as one. So each step count as one. So shortest path I can calculate, and each path is count as one. So that is the shortest path algorithm. In the shortest path, how could I in an undirected graph, if I have to find the shortest path, what is the best? That is the DF. Sorry, DFS is the best. DFS is the best, and DFS is the used for longest path. Like in the graph, what is the longest path present? Like here it is this, and this. This is the longest path. So that is a different story actually. So that's why like this is why we for BFS I will use BFS for the shortest path algorithm. Okay, hope you understand the problem. Okay, and last example, let's see what is the last example. 4, 6, 8. 4, 6, and 8. So in the 4, 6, 8, what is this? 4, 6, sorry, 4, 6, 5, and 8. So there is there are prime number, but there is I cannot directly hop. Like 4 to 6 I have to come, then 6 to 5, then 6 to 8. It's 3 hop. This is the maximum hop, and this is the minimum hop as well. So again, I have to take 3 hops. So there is no alternate way. So this is what you have to do. Now, what we are taking, what we are checking. So uh, let's take an example. Let's take an example. Why did I remove that? That is actually a good example. So I should get back the example. This is actually a good example. Let's take this is as an example. Okay, copy. Okay, let me uh, redraw this in a good way. Then I will again use on the video. Okay. So this is the example I just simply modified. So I am assuming with this example I can give you all the cases, all the edge cases as well. So this is the normal, like this is a single, you can see this is a, instead of single line, I write in this way, okay. This is a single line, this is a normal path, like 2 to 7, I can go 7 to 3 or 3 to 7, this is the normal way. Now I'm drawing the special way, like 2 is the prime number. From 2, I can go where? I can directly go to this 4, this is on path, or even 4 to 2 I can come back. Similarly, this 3 I can come here. Also I can go there in this place, right? Similarly, another edge is there. From 2 to 8 is there. This is where I can go. So these are the path. Okay. So let's see how could we reach from my start to end. What are the outcomes are there? Okay. Okay, I can't take this because this is the shortest path, right? Earlier example, that was the shortest path. Okay, let's make these things difficult, like a little difficult. Okay, fine. We are getting shortest path. I'm adding more nodes. So here I want to get node, like I'm making 1, 2, 3, 4. So I have to make this thing as 5. So I have got 3 elements here. Fine, I will add 3 elements here. Okay, okay, let me pause and redraw the image. Okay. This is the graph. Okay, now let's see, is there any fault or not? Okay, now let's draw our special jumps. The 2 I can directly go to 2 to 4. This is one jump possible. 2 to 8 is also one jump is possible, right? And 3 where can go? 3 I go to 9. 3 I can go to this 9. Right? Any other jump? This 5 to 15 I can go. This 5 to 15 there is another step. Is there any other thing? Notice? No, I guess nothing. Right. Okay, 3 to 15 also there is a jump. It's 15 to 3. Okay. So 1, 2, 3, 4. 1, 2, 3, 4. Okay. 4. Okay. Anyway, let's find it out. Like what are the minimum possible cases? Okay, so minimum possible cases, there are two actually minimum possible cases. So we see what are the cases. Normal is this way, right? This way. I can reach. This is the hardest way. So any shortcut? Let's see. From 2, 2 to 7, 7 to 5, 15, 15 to 5, 5 to 3, 3 to 9. How many steps? Let's see. 1, 2, 3, sorry, 15 to 3. Yeah, I can do that. Actually, this is a indirect graph. Like this is actually direct graph. 3 to 15 I can jump, but 15 to 3 I can't jump actually. 15 to 3 I can jump. This is actually directed. This path is some places directed. Some are non-directed, but some are the directed. Like from prime number to any other number, these are the directed graph. You cannot jump at a random. Like 15 to 3, I can 3 to 15 I can jump, but 15 to 3 I cannot jump. Okay, so these are the directed graph. Okay, so now see, like 2 to 7 I count, 15 come, 17 come, 3 I can count. How many steps? 1, 2, 3, 4, and directly here 5 steps. Any shortest path? Here I can come at 2, 2 to, there is direct path, and 2 to 8, 1, 2, 3, 4, and 5. No shortest path. Okay, let's see in other places like 2 to 4 I can come, 4 to 5, 1, 2, then 3, then 3, 3 I can come 3, and 3, 2, at 9 I can come. This is the fourth step. But here I have to do 3 steps, 5, 6, 7. Longest path. No. Any shortest path? Now this is a 2, can come at 4, 4 to I can go 5, 2 step, 3, 3 step, then 9 directly, 4 steps. So within the 4 step I can reach. Okay. So this is the shortest path. The shortest path here is 2, then 4, then 4 to 5, then 5 to what, 5 to 3, then 3 to 9. Okay, so we can use BFS here. So this is why BFS is help to find out the shortest path. Even though it is a directed in some places, but it will still help you. Let's see, BFS you all know. Like if you don't know BFS, please watch the BFS videos, because without that you can't able to understand this problem. So this is BFS, we do a queue mechanism, right? Queue mechanism. So until my queue is empty, I have to iterate travel. So initially I put my index at let's put the index position as well. So index position are, let's see, all of red color 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. This is the index position. Okay. So here I am usually in a BFS we put 0, but here also I need to count the step as well. So I am putting 0 in the step number. Okay. So currently my index position is this one, right? So 0, 0 I will put it there. 0 is the index position, 0 is the step. So I am reaching at the 0th index at the 0th, but I say 0th step. Okay. So where from here, from 0, where can I go? I can directly move, and I need a visited array as well. Okay, visited array. Like if I have already visited, I will not visit that array, that place again. Okay, so by default every visited array is false, so by default everything is false. Okay, so I'm not writing false everywhere, but I have to do for 0 1 12 3 4 5 6 7 8 9 10 11 and 12. So this is my 0 1 2 2 3 4 5 6 7 8 9 10 11 index. Okay, got it, understand. So I will first put 0 0 0 0. I am first putting at the initial level. 0 0 from where I can go 0 0, I can go where I can go 7. So I will add this thing as 7. So I will first 0 I have visited, so mark this thing as, this is the visited array, this is the visited array, like visited array. Initially, as everything is false, I'm not writing, and initially everything is false, that's why it is empty. So 0 0 I have put it in the queue, and I will put as visited. From 0 to 0, where can I go? I can directly go 0 to 7. Okay, I'll include 0 to 7 here. 0 to 0, not 0 to 7, like index 1, and cost is will be increased by 1, because so okay, let's start from the beginning. So everything is 0. I'll put 0 0 0 0 my index, and and I have to mark this thing as true because I have visited. So every time I pop one element, so this 0 0 will popped out. So my current index is 0, and current step is 0. Okay, so now from this index, which from to which index I can move, that index I have to add into the queue. So I can add to the 7th. The 7th means index 1, and with the cost step plus 1, step is 0, this is 1. So then again what I can do, I can go, see here, from 2 I can go this place or this place or this place. So I can come back to at 6. So 6th index with a cost of 1, and 7th index also cost of 1. I can reach in this index, right? So, and what is then my, can I go any other places apart from these three are my current position. I cannot go any other places, so I will stop. Next step, I will, and these three cases I will put mark as 2, because this is already visited by whom, visited by 2. Okay, so done. So now where can I go? From, I have to now pop again one element, so it is 1 1. So 1 1, so current is 1, step is 1. From this one first index, where I can go? I can go to 0, but 0 is already visited. So I cannot, if it is visited already, I cannot go back to there. So I cannot take this, but I can take 15. 15 is not visited yet. I can take 15. The second index I can take. So I'll add second index. Second index with the cost of step plus 1. Step is what? 1. So it will be 2. Got it? And again, this index I am visited. So I will mark as 2. Fine. So from 7, can I go any other places? No. Right? Stop. So this is done. So again I have to again push one element, 6 and 1. It becomes 6 and it becomes 1. So 6th means where? 6th. And this is the 6th place. From 6th place my step is also 1. The 6th place, where can I go? I can go 5, I can go 7. Okay. So 7th element. 7 you can see 7 is already visited. So I cannot go back to 7. I can go to 5. So I will add 5. So I am adding what? I am adding 5th index with the cost what? 1 plus 1, right? So 2. 1 plus 1, so 2. So adding 2, and I have to make this 5 as visited because I already visited this 5. So now what I have, where I have to go? Now I have to go where? Now. Okay, so 2 to 4. Okay, so now this 3, and this is where I am going now, where I am going. So now this is up to 7 1. So 7 on 1. So I am this 7 I am here, and 1 is this. So I am popping 7 and writing it there, current and 7. So 7 where I am there. 7 where can I go? 7 I can go 6, I can go 8. 8 is visited, not visited. So I can add 8. So I am adding 8 here. 8 with the cost of what? 1 plus 1, 2. So 8. So 8 I am marking as visited. Can I go anywhere? 6 is already visited. So I can't go to 6th index. So now my next index is 2 comma 2. Now I am popping this 2 comma 2. So 2 comma 2. So from 2 comma 2, 2 is what? This is my 2 comma 2. Where can I go? I can go to third index or first index. Is there any special graph? No, right? No direction. So I can go this one or this one. Okay. So what are the cases? So in this case, what is my thing? My thing is I can go either left or right. So left is already booked, like 1 is already visited, so I will go to 3. So I will mark this thing as 3. 3 comma, what is the cost? 2 plus 1, 3. So 3. So I have added, and 3 I am marking as 2. Okay. So this is done. So what is the next step? Next step is 5, 2. So 5 it will come and 2 it will come here. Okay. So 5 and 2. 5 and 2. So 5 in 2. So from 5, where can I go? From this 5, I can go. See, 5 is a special case. 5 is a special case. 5 is a normal. In the 5, I can go this side or this side, and 5 is a prime number, so I can jump as well. So if it is a prime number, I can jump. So there is a one condition I have to check. If it is a prime number, if it is not a prime number, like 15 or 4 and 8, these are not prime numbers, so I can simply go to left or right. But 5 is a prime, so there is a special case. I can know this thing. From prime number, I can go to special case. So I have to somehow find out, like from 5, what are where places, in which places I will go. I will come this thing later. Like from 2, how could I know, like I can come to 4 or I can come to 8? Or from 3, how could I know I can go to 9? I can go to 9. So this is, you have to. We have to know somewhere. Like for right now, forget this. How could I go to 4 and 8? Right now we know we can go. So that's why I'm writing. How could we go? We'll think about later. Okay. But now what? 5. 5 from where I can go where? 5 from here I can go to 15, right? 15 is index 2, right? Index 2 is already visited. I don't can go there. I can go index 4 as well. If index 4 is not visited, I can go index 4. Index 6. 6 is already visited. I can go 6. So 5 I can go where? From 5 I can go index 4. Index 4 with cost 5 is 2. 2 plus 1, 3. With 3 cost. 5 is also done. So next I will put 8 comma 2. 8 comma 2. From this 8 comma 2, where I can go? See, 8 comma 2, 8 is a non-prime number. So I can go left or right. So from 8, here I can go 7th index. 7th index is already visited, so I can't go there. And 9 index, this is the place. I can go 9th index. So from this 8 comma 2, I guess 2 places. Sorry, single place. Like here only 9, because 7 is already visited. So I will simply write add 9 here with the cost 2 plus 1, 3. 3 cost. And it is already visited 9th index. I am marking this thing as visited. Now this 3 comma 3. From 3 comma 3, where I can go? From 3 comma 3 is nothing but 17. This is the 3 comma 3. I can go to 4th index, or 17 is a prime number. Okay, so there could be a special case. So I can go left or right and no special position. So is there any multiple that are any multiple of 17 present? No, right? So only left and right. So left is 2 and 4. Left is 2 and right is 4. 2 is already visited. 4 I have, I guess, already added here. I mistakenly from 5 to 4 I have already visited. 4 is also visited. I forgot to mark is here. 4 is also visited. So here I can, this is visited, this is also visited. So I'll not move there. This I am actually saying about the BFS algorithm. Okay. So this is already visited, so I cannot go there. Now 4 is also done. 4 comma 3 is also done. Next is, sorry, 3 comma 3 is also done. Next is 4 comma 3. I forgot to update here as well. So earlier it was 3 comma 3. This is also done. Now it is 4 comma 3. So it is 4 comma 3. In 4 comma 3, what are the places I can go? 4 is in the fourth index. What is the value? 3. It's a special. So I can go left and right. And the special cases, I know like it is a special case. There may have some options. Okay, there may have some options. So there are actually 2 9s are there. So 9s here is there and 9 here is there. So another thing is I have to calculate here. So I have to know like how many 9s are present. So that is also I have to find it out, like how many 9s are present. So that I have to make a list and already store that thing. Okay. So that means I have to find out the how many 9s are present. Okay. So it is also helpful in future actually. Otherwise, if I get only 9, so there are actually 2 9s are there, right? So if you don't know what are the index position, I have to iterate every times and find out 2 9s. So what we could do initially, starting of this kind of calculation, we could do what? We could do just iterate one times and store in the map, one map or dictionary, and store the each unique item and its corresponding index position. Okay, so map pointing to a list. So int to a list or vector or list. This is the case. We have to make a map of this. Okay, so and for each item of 9 I have to point it out. So 3 I can go where? 3, like third index. For fourth index I can go third index to fifth index. The third and fifth is already visited, I can't move there, but I can go which places? I can go 8 places, but 8 is also visited. 8 index is also visited, so I can only go to 11th index. Okay, 11 is I'm marking as this 2, and this is 11 comma, and which cost 3 plus 1 4 cost, right? So this is the fourth cost. Now even though I reach this position, but I am still traversing until or unless my current becomes my n minus 1, I have to traverse. So 4 comma 3 is done. Now 9 comma 3. So 9 comma 3, 9 and 3 becomes here. So from 9 to 3, where can I go? From 9 I can go where? 9 I can go where? 9 to again 7, and 9 is a non-prime, so it is only two possible, 7 or 9. 7 is already visited, 9 is already visited, so I will not move. I'm not going any six spaces. So after that, sorry. 9 is ninth index. Sorry, 9 index. From 9 I can go to 10. I can go to where? I can go to 8. 8 is already visited. 10 is not visited. I can go to 10. So 10 I am marking this 10 and adding this thing into here. So 10 is 9 10th index and 3 plus 1 fourth cost. Okay. Now what I can do? Now it is 11 comma 14 4 11 comma 4. Whenever I got 11, whenever I got n minus 1 index, then time return the number of steps. So number of steps are returned. So this is the 4. I guess you got it. You understand the entire flow, how it is works. Okay, so two things we have to now find it out. First thing is what it is we got, like if there are multiple lines, multiple of the same number, we have to find out or figure out what are the same items are present, right? Same items are present. So in that case I have to initially I have to iterate entire thing. I'm iterating entire thing, and I'm marking this thing as in a stored in a list. Okay, this is the one case. Second case is comes in the picture, like how could I know what are the uh, special jumps, like from 2 to 4? How could I know? From 2 I can go, from 2 to 8 I can go. How could I know 3 to 5 or 15 I can go, or 15 here I can go? What are the special cases? So if you are thinking about that, calculating the prime number before and after that iterate to each and each element to find out this multiple, it is not really well, because what you are thinking like 2 is a prime number, now iterate for every number and see what's divisible by 2. So this is the case, you are iterating every time. So again for 7 you are iterating every time, for 15 you are iterating every time. So it is, if it is possible, like every element is a prime number. Okay, or very few, like here you can see only how many are there. 12 items are there, and among them only 1 2 3 4 and 5 from 7 items are prime number within this 12 element. So it is a big of nearly n square. So in terms of n, it will give you becomes n square. It will give you TLE. You can't go there. How could I then find it out? I can do one thing. I can do. I can run from 2 to this. I will taste a multiple of 2, and I am already storing the each item in the list, right? As I told you, I have to store if there are multiple the same number may present, right? So I have to store the unique item and its corresponding index positions. So there will be a list, there will be a map or dictionary where I am storing unique item like 2, 7, 15, 17. Each and every item I am already checking, right? So what we will do, we will start from 2 and check the multiple from 2 to 4, like 2 I can check 4, then 6, then 8, then 6, 10, then 12. This is how we'll start checking. Okay, so up to which we will check, up to which, like when it will cost, we have to take the maximum element, like from the maximum element we have to take it. But like maximum element, actually you should know this thing, because I'll explain you why. Like you have to calculate the maximum element of the list. You need to find it out. because there is a I'll explain you why later. Okay, for now you have to calculate the maximum element. So up to maximum element I have to traverse. So 2, 4, 6, 12 up to 18 I have to check, and within this 9 loop I can get, like, this is the cases. Most of the times, like, I have to check. You will understand, like, it seems like we're traversing too many times, but think of it. For 17 into 2 for 34, 17 into 34. 34 I will check in the map, but 34 is not present here, right? So the loops end here. And a single check is fine. For two, only for two, it will be too many checks, because most of the value, any even number can be multiple of two, right? For other prime numbers, the whenever I come to 17 or this kind of value, 17, 13 or 19 itself, they're double. They're next multiple. Like 17 is 34, 13 is 26, 19 is what, 38. Their multiple doesn't exist in this entire like in the maximum. I have to check from starting from 2 to their multiple, or I from ith multiple to maximum of this array, right? So most of the item will not present in this cases. So that time it will take big of one time. Okay, so that's why the time complexity will be adjusted. Will be adjusted. Hope you are getting it. Okay, so this is how we have to check. Like, then, so every time if I get a prime number, I have to check the multiple starting from like, if it is ith item, I will start from I into 2 and checks. I will take like incrementing the value of the I with the multiple. Okay, let's assume my prime number is p. So I will start a I with a prime number of p cross 2, and every time incrementing by p, like p cross 2, then next item of p cross 3. So it will be incrementing p cross 2 plus p is what? P into 2 plus p is nothing but 3p. Similarly, every time it iterating by p element. Okay. So every time to check this element and check whether this 2p or 3p, this kind of thing will present in the map or not. That is the case you have to check. In a map, you can get a big of n time, log n time. So I'm assuming sometimes it is, some of the places it will big of 1, some of the places it is big of log in the map. You have to check in the map. So this is okay for me. That's okay for me. Okay, so login is okay for me until we touch the n square. It is okay for me for right now. Hope you are getting it. So this is the my work process. Okay, now let's start the running the pseudo code. Got it? First, you have to find the prime sieve, like what is called sieve of Eratosthenes, or you have to find it out the all the integer present in, sorry, all the primes present in the array. Okay, for this the most suitable approach is sieve of Eratosthenes. So this for this thing, you please watch a video on this specific topic, sieve of Eratosthenes. Or you can see also my video, but it doesn't matter. You can watch any other video. Just understand the logic what it does. Because if you want to calculate what is called, like, there is a n number present, right? So from 1 to n, you have to calculate check each and every prime number. Each prime number take minimum of roots n square times. So n I have to check n items, so it will take n into square root of n. So it will take it is a huge time. Square root of 10 is it's huge. It will actually leads to your problem to TLE, time limit exceed. So you can't do that. For these cases, we can do big like, if you use C of Eratosthenes is from 1 to n number of cases. So each cases the time computation reduced to 8 into log of log n. So this is much lower value than this n square root of n. So that's why we are using sieve of Eratosthenes. And the sieve of Eratosthenes, for this reason, we need a maximum admin, like up to which I have to calculate, up to which number I have to calculate the prime number, right? For this way, we have to use the maximum. That's why I told you, anyhow we need to calculate the maximum. So this is the maximum we have to calculate. So what I am saying, what we have to do first, obviously, first step would be my calculate the length. That is a normal step. Calculate the length. So the first step is, like, what is the problem is minimum jump. Let's say minimum jump function name is min jump, minimum jump. For this I am finding the algorithm. What is passed? Nums array is passed. Okay, so let's start the pseudocode. This is the thing. So very first step what to do, usually I calculate the n, length of the array. So n equals to nums dot length. Okay, this is how I am calculating. After that I need the maximum value as well. So that's why my one item, let's say maxi is nothing but max of this. You can, if there is any function, you can directly use it. If you don't need, just iterate one and you can get the maximum value. Maximum of nums, simple, and get the maximum value. Now what I need a prime list. So that's why I'm using the sieve of Eratosthenes. So here I am calling one function like primes. I will use sieve of, or saying make sieve. So make sieve. This is where I am implementing my sieve of Eratosthenes. Sieve of Eratosthenes list. If I give you a list of, I'm passing a n. So what it will return? It will return a list, so return an array of n plus 1. That means 0 to n items, 0 to n items. And in this list, we will get either 0 or false is there. So if it is a prime number, it will be marked like its corresponding index position is marked as true or false, or 0 and 1. This is how it returns. So it will return me a length of n. So that's why I am, and not the n actually, I have to pass the maximum element, not n, maxi. So n could be anything. N could be like let's say 2, 4, 8 and 31. 31. So I have to calculate the prime between 2 to 31. Okay. If I calculate n is 4, if I calculate only 2 to 4, like 4 is the prime. So up to 4, how many primes are there? Only 2 and 3 are primes are there. But I have to find the 31. The 31 could be also prime number, right? So that's why maximum, up to maximum, I have to calculate the prime number and pass in the sieve of Eratosthenes. Got it? Okay. Next. Next, what I told you, I have to calculate, like I have to find out the each unique digit and the corresponding index position, right? For that I need a map, or you can say dictionary or hash map or something. Okay, so I am saying creating a map, map of, let's say um, map of our integer array, integer, and it is of a vector array list. So I'm writing as list, array list or vector, anything you can understand. So it will, I am creating a empty map. Okay, so this is what I am doing, and I have to iterate to each and every item to calculate what is the what is called the index position. So what I am doing here, for each item, for I equals to 0 to I less than n, then I plus plus, I'm iterating to each and every item. And what I am calculating, I am calculating nothing but what is called map of my that nums of I and dot add, and adding what, the current index position. This is what I am doing. Got it? Okay, and assuming you got it. Okay, now let's start about our BFS algorithm. Okay, let's start right, our BFS algorithm. So for BFS algorithm, simply I'm doing what, I am minimizing this thing, because BFS algorithm will take a huge line. Special BFS it is. You understand why I'm saying. So what I need actually, so I can directly write it here as well. So I need for BFS algorithm, I need some things. I need one visited array. So one visited array of size n. So let's say array 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 of size n, and I'm, what was I am initializing with 0. 0 means false. That means anything is not visited. So this is my visited array. Okay, and after that I need what, I need a queue. I need a queue. So queue is nothing but a queue data structure. Queue. So this is a queue. Okay. So first step will be of mine. First step will be adding the value into the queue. So which space I have to add? I have to add like 0th index. So q.add 0, and so another 0. Why 2 0 are there? Like let's say I'm inserting a list. Okay, so I'm inserting a list 0, and first is index, second is the step. Step 2 reach out that index. So initially I'm 0th step, and state is equal to each 0 is 0. So that is what, and I have already visited my 0th index. So that's what I'm writing, what visited of 0, visited of 0 is 1. I have already visited, right? Because I'm adding to the queue, that means I am visited. So that's why I'm adding to the queue. So that's 1. So what? Right now, what I could do? Now, as I told earlier, we have to iterate for each item in the queue. So what we have to do? I'm writing in this here. So while my queue is not empty, so not equals to queue dot is empty, or any function is there, is that thing is empty. If it is returned false, that means I have to if it is returned false, this part return false, which becomes true. It means unless my queue is empty, I have to do these steps. Okay, I guess you are getting it, as I discussed earlier. Okay, and I guess you are getting it. Understand? Now let's like now I have to do what? I have to pop the element from queue, and from popping I need what? Let's say element I am popping. From element or node, I can say one node, or one node I can say. So node I am popping, node equals to q dot pop. Okay, you can pop that. But node is not only node, so node is what is current index. So I'm writing as idx. So idx is nothing but node 0, and current step, right? Current step, current step. So current step is nothing but node of 1. Simple. I guess you got it. Okay. So I did the. Now what I have to check? So simply I will simply check if my node is already I am 1. So as I told you, if I am already in my n-1 place. So if my index is already n-1, so directly return. No need to do anything. Return, and this is a directed graph and connected graph. So anyhow you will return, you will reach to this step some after sometimes. So reach step. Okay, simple. Got it. Now what I have to do? Now where I can go? I can go left and right, I can go these places, right? So what I have to do? If my index is n-1 and sorry, i-1 and i+1. So I will write as if my index, if I will check first is index is out of range or not. So index -1. So index -1 is greater or equals to 0. So it is not out of range, and my it is not visited. If it is visited, why should I add it? Right? Visited. It is not visited. So visited of index -1 is what? Sorry, index visited of index -1 is equals to 0. If it is not visited, then only I will do something. Correct? So I will do what? I will do simply I will add into the queue. So dot add q dot add. I'll add what? I will add index -1. I will add index -1 and also step +1, current step +1. So let me name as step. It's too long actually. Let me name as step. So step +1. So step +1. I can go. And another thing I have to do what? It is already visited. Earlier it was not visited, now it is visited. So visited is, I have to mark this as visited, index -1. So I have to mark this thing as 1. It is visited. So this is the if else case. So let's see what are the next case. Next case will be exactly kind of same. Let's now copy. So +1 case. Index +1 case. Okay. So index +1. So again I have to check if index +1 is inside my n. So index +1 is inside my less than my n, and index +1 is equals to 0. If that's the case, I will simply add index +1, step +1, and visited of index +1 as 1. Simple. Now the thing appears. If it is a prime number. If it is a prime number, as I told you, if it is a prime number, there could be multiple cases, right? If there is a prime number. So if my prime, if my number is a prime or not, if my prime number, I return, okay, wait a minute, where I can see from my prime number or not, from here, this primes, right? So if it is a prime number, if primes of that nums of x, nums of, not x, nums of idx, index, if it is a prime number, then I have to do couple of things. I'm right now assigning the value as prime. Let's say p equals to is a prime number. So p equals to nums of, because you understand why I'm writing, because I'll have to use this p many times. So that's why I'm shortening this. So p. So if it is a prime number, what do you have to do? I told you, if it is a prime number, I have to check its multiple. So I have to start with multiple, and I have to check whether multiple is present, like if multiple is present or not. If it is present, then I have to go to each and every multiple. Okay. So for my, let's say, multiple, start with prime number. So actually the 7 also can also denote 7, right? 7 go to any place is a 7. 7 is also prime number, right? So I will start. I'm not, while I was explaining, I said 7 into 2, but it should 7 into 7, 7 into 1 actually. So I'm starting from multiple. How long I have to search? Until my multiple is less than or less than my maximum, less or equals to maximum. So maximum I stored where? Maximum I will store in maxi. Yeah, maxi. So maxi and I not multiple plus plus. So multiple plus equals to p. Okay, multiple plus equals to p. So this is what I have to do. Okay, so what I have to check? I have to check whether this current multiple is present in this here, where in this map where I am storing the occurrence. If multiple is present in the map, I'll iterate, like I'll add every index of that specific number, also specific multiple. So I'm writing a shorthand again, like if this multiple, if multiple in map, just write as according to your own coding language. If it is in map, then I have to do what? So there are multiple elements and it is an array list, right? So for each element, so for each element, like for each element inside this map of what? Map of multiple. Each element of this map of multiple, I have to iterate and I will do what? Simply that what I was doing earlier. I'm adding to the queue. So I'll add into the queue. So queue dot add one case, q dot add element as well as like what is the thing, that is step plus one, step last one usual, and this is also visited. So of element visited of element equals to 1. This is what we have to do. Fine. So this is the loop's end here. So for loop ends here, if condition ends here, outer for loop also ends here, and this element also ends here. Okay, got it. So this is the case. This is the whole pseudo code, and you can see like my function is also actually ends here. The main function mean jump also ends here. So I'm not, you can, if you notice, I'm not returning anything. I'm not returning anything, right? So why not returning? Because I'm returning here, see here. So this is a connected graph, and anyhow I'm going to do the last index. So I'm not returning anything. When I'm going to last index, and then from that point I will return it. Okay. Now there is a catch. Now there is a catch. Let me explain. This is a very edge case. Until or unless you face the edge case, it will not come to your mind. This is a very edge case. I'll explain the edge case. Just a minute, let me take the example. So assume this is the case, like 7, 7, there are multiple 7s are present. Assume this is the case. So in this case, what is the thing? Like if I do the BFS, it is 7, 7, 7, 7, 7, and it's like connected, each and every each and everything is connected. Like this special graph, it's a kind of a special card, which name is as complete graph. So this is a complete graph. So if I get 7, so do I have to again go to 7? Like here, what is the 7? If it is 7, my map will store what? Map will store everything like 0, 1, 2, 3, 4, like everything it will store, right? So if I iterate, like assume that only this many graphs are there, 5, 5, 8, okay? So assume 5, 6, 7s are there. Only 6 sevens are there. 1, 2, 3, 4, 5, and 6. These 6 sevens are there. Okay. So if these are 6 sevens are there, so if I am calculating this step, I'm connecting this one, this one, this one, this one, and this one, right? I'm adding it to the queue. So because I am iterating each item in this list or in this in the map. Okay. So do I have to do any another thing? So thing is already added, right? The thing is already added. Like these thing, okay. If it is my queue, in the queue, right now I'm just adding the index position. So I'm checking out the 0th index. The 0 will be popped out, 0 will be there, and I will add that other index. Like queue, I will add 1, 2, 3, 4, and 5th index, right? So right now when I come to in this index, again I will check, I will get 7 is prime. Again I'm going to do what? I am going to the thing is I can't add it because everything is gets visited, right? So visited will mark as true. But the thing is I have to iterate. There is no other way. I have to iterate. So every time I iterate, and it will take time complexity, and it will get to n square. But because for each item I am checking entire array. So isn't it? So as in only these are the items present. So for each item it will go to entire array. Right? So it is a big of n square. So for I have to checking each and every item, right? N square. So in that case, and see this is one case, see one thing, when I'm checking this map, the map I'm checking only I'm checking the map whenever my item is prime. Whenever my item is prime or number of IDs is prime, then only I am checking into the map. That means what? And one thing, if I visited one prime number, if I visited one prime number, do I need to check another prime like is corresponding? No, right? If I get prime number, I already visited this is corresponding index position. Like so I'm starting from multiple from 3. So all the prime number I am visited, right? So after this thing, I can make this thing as a non-prime. This thing as a non-prime. I can make this thing. So what I could do, I can simply do after this thing is done, after this thing, this entire statement is done, before ending this thing, I can simply write prime like IDS index, but not IDS index. My what is prime? What in array is containing my index? It is primes, right? So I'll do what primes. So primes primes of p, I will make this prime number as false. I'm making this thing as a false. Got it? So this is what I am doing. So if I make this false, like every time now I will pop at fast index. Fast index, I'm getting what? 7. Now 7 will come here. 7 will try to add this one and this one. That is okay. It's fine. This two will take big of one time. So this is fine. But whenever it will check whether it is a prime, it will get 7 is not right now a prime. Earlier it was a prime, but now it is not a prime. So for it is not a prime, it is not going to insert and iterate through each and every element in this prime number, right? So that's how I can save the time. I can save the time. If it is 7, assume there are less number of 7. Okay, 2, 7, 6, 5, then 7. Let's say 7 appears one, then 5. So see what 7 appears twice. So only earlier, whenever I'm iterating in the map, 7 is pointing what? Let's say 0, 1, 2, 3, and 4. So 0 and 4 it is time. So I'm already added 0 and 4, right? I've already added 0 and 4 in my queue. So when I come in this index position, should I add again? Like, should I have to iterate and check how many sevens are there, or how many sevens are not there? I've already done it, so I shouldn't do it in anything again, right? So this is why I'm doing this for only for 7 or any non-prime number, just because again I'm saying this thing because I am iterating the my map only the number is prime. So if it is 2 is like if so 6 is multiplied 6 times, right? So in that case I'm only doing these two steps. I'm not iterating 6. Like if it like, assume this is my 6, 6, 6, 6, 6, 6, all are 6, right? So in my map also it is showing 0, 1, 2, 3, and 4. Now I am adding the queue. I am adding to the queue at equals 0 to index. So 0 I am adding. So I am adding 0. 0 in the queue. I'm adding 0. In the next time I will pop this 0 and I'll do what? After popping the 0, 0 is not a prime, so I'll do this just plus and minus. I'll check index plus 1 and index minus 1. I'll not check it's all position of the 6, right? So again I'll go here, go here, go. So it is big of 8, big of n. But here as 7 is a prime number, I will go inside the map and check the occurrence of 7 and 7's multiples, right? So if that I'm checking, I've already done it already. I've already done this multiples. Like if there is 14 also there, so 14 also I've already added into the queue. If there are, assume, let's take another example, there's 7 and 14, 7 and 14 are there only. Okay, so let me remove everything. If I am doing this, like assume one case like only 7, 14, 7, 14, 7, 14, all are there, like 7, 14. This is the end, like 10 to the power 5 or 10 to the power 3 items of there. 7, 14, 7, 14. Like for 7, I have already done, like there is multiple is 7 is there in the map, and 14 is also multiple of 7, so it is inside the map. So for when I got a fast 7, I've already included everything in my queue. So no need for checking for again for 7, right? No need for again for checking for 7. So there's the reason. After I got one prime number, I'll not iterate this primes or is corresponding multiples in again, because the first time only I added all this multiple into the queue. So next time I don't need to do that. So that's why that how is what is the easiest way to not to do that. So I will make the 7 or this prime not as a not prime number, just mark as a not prime number. So even though it will come in the next iteration, it will not come into this inside this if statement. And if it is not coming inside the if statement, it is not checking the multiple. Got it? So this is the what we have to do. Like this is one edge case. This will not come to your mind until and unless you face the problem. Okay. Now see what are the time complexity. Time complexity. It's a good question. Right now, this here is a big of one. This sheet takes big of n log n. This is a n. This is a log n. This is a time complexity of this prime sieve. Okay, calculating the sieve. Okay, here it is a sieve. Okay, so it is a big O of n log n. Now this in this, like I have to iterate for each and every item, so it is big O of n, and this is all my big of 1 steps. And after that, this while cube is not empty. What we are doing actually here? Let's see what we are doing actually here. Here in the loop, up to this is big of one, big of one, correct? And here what I am doing, it is a multiple way of checking, and I'm assuming it has n element, like one prime has n elements. So it is a log of log n. I'm assuming the multiple, like n multiples are present. So it is actually log of log n. So it is nothing but this. It is nothing but log of log m. Okay, and how many times this while loop occurs. So we know what we are iterating each and every node, right? Only the node. Even though it's a v plus e, if it will work like here, I'm actually iterating each and visiting each and every node. That's all. Like this is also big of n, big of n. Okay. The thing is here, it is not big of n because time complexity of BF is actually big of V plus E, right? So V plus is means V is the node number, E is the ages. So here I'm ignoring the ages. Okay. So it is if it is a n or 2n of ages, assume there are n nodes and 2n ages, right? So even though it's a big of n, right? Big of n, isn't it? That's why I'm saying this while loop will like is what is called BFS will take big of n time. So inside this we're going this log of log m. So what is the time complexity of it? The time complexity is earliest for sieve. It is log n log of log n, right? Plus n into log of log n log m. So obviously this is better. This log of log n is better. The time complexity becomes big of n log of log n, correct? And the space complexity, am I taking extra space? Obviously, for sieve, for queue, and for this what is called that storing the our nodes value, like its index value and its unique value of each and every digit and each and every places of this array and its corresponding index position, this map. So that is also I'm taking. So that's why I'm taking big of n times. I'm taking not n square, big of n. I am storing it. So this is all. The code is actually very long code it is, but the thing is, it's too easy. Like everything, this entire part is nothing but BFS, and this part is only our normal steps. Like this is sieve. Sieve, I will upload the code in the my code, and sieve you have to understand from other videos because it will take another time to understand the sieve problem. But it is very useful. Please watch this video, understand the sieve, or at least understand how the sieve works right now for now, and this is the simple BFS code. Even though the calculation is very high, too much codes are there, but it's simple BFS code. Okay. Okay, then this is all about this video. And if you find any mistake in this video, please comment it down so that I can rectify it. And if you find any useful video on this topic, please let me know so I can also learn it. Thank you. Bye bye.